Okay, since it's the 3 p.m. already, we can start now. So, our today's right now we are in the week 11 of Introduction to Material Science and Engineering course, where we have covered the few list of the content. Those are as follows. When we discuss about the crystal resolves yesterday, that too we discuss in the week 10 also. This time we compared with the theoretical and the experimental value, and we saw that there is a lot of disparity in between them. The order of 10 to the power of 3, this somewhat in their values, theoretical and experimental, this much value difference is there. And we saw that we know that why it has happened, that's due to the presence of dislocation. Then we see the strengthening mechanism we discussed. We see what is the dislocation density and how do we calculate them. And then we discuss about the Frank rate source, how the dislocations are generated within the material during the process of, we can say, plastic deformation. Then the strain hardening we discuss another strengthening mechanism, dislocation interaction. And then we discuss about the solution hardening. Then grain size hardening. So we discuss a list of the strengthening mechanism. After that, we discuss about the edge hardening. Mostly we are focused on the aluminum alone. Then after that, metastable precipitate that has been formed in this particular case. For example, GP zone, theta double dash, theta dash. Those are the metastable phase. Those are the metastable because those are not present in the phase diagram. Later on, we discuss about the annealing of the cold work state, cold work metals. In that, the entire annealing process is divided into three parts. One is recovery, recrystallization, and then grain growth. So this particular week, the list of the content are as follows. Before we proceed further, let me ask you that do you have any doubt in this particular content? If yes, we can discuss them. If no, we'll go to the question solving. Okay, since there is no doubt, let's move ahead to the question number 1. We'll start with the true and false type of questions. The question number 1 says that theoretical CRSS matches the experimental value for the most metals. What do you think? What is your comment on this, that the theoretical CRSS value and the experimental value, they are matching each other? False, right? There is a huge difference in between them. Let's go to the question number 2. The dislocation enables slip at lower stress by localizing bond breaking. Localized bond breaking. What do you think? Dislocations enable slip. That's right. At lower stresses by localizing bond breaking. They are talking about from the perspective of why the theoretical and the experimental value are different. It is happening because of the dislocations present in the material, which can at lower stress itself they can lead to the bond breaking. Again, the term localized means that they are happening where the dislocation is present. True. Very good. The dislocation theory was proposed to explain why crystals are stronger than predicted. Is it false or true? Dislocation theory was proposed to explain why crystals are stronger than the predicted value. False. It's the other way around. Okay, let's move ahead. Slip wire dislocation requires simultaneous breaking of all the bonds on the slip ring. Slip requires simultaneous breaking of all the bonds. False. Again, we use the term localized, so slip will occur by the localized breaking of the bonds, not the entire bond breaking. Okay, so false, true, false, false. Let's move ahead. Let's move to the question number 2. Which of the following is not a practical strengthening mechanism? Not practically possible. Option B is the right answer. Perfect. If we cannot remove the dislocation thoroughly, they are present by the way we create them. In the manufacturing process itself, the dislocations are being created, and it's not possible to remove them. Well, the strain hardening, grain size refinement, and precipitation hardening, these are the method by which we can strengthen the material. Let's go to the question number 3. Dislocation density is defined as number of atom per unit volume, length of the dislocation and per unit volume, number of slip plane in the crystal, density of the material in the dislocation region. We want to find the what is the dislocation density. Defined. Okay. Very good. Option B is the right answer. That is the length of the dislocation per unit volume. So its unit would be meter per, length is meter per meter cube. Few people also express it as the millimeter per meter cube. Sorry, mm cube. So both are correct. Let's move ahead to the next question. Question number 3. Sorry, question number 4. Now it's come from the lecture itself. A well annealed material. A well annealed crystal has a dislocation density of approximately. The specimen is very well annealed. We heat it to the very sufficient temperature which is required, and we hold it for the long time. That is the process of annealing we have discussed in the previous weeks. So here, for the well annealed materials, they should have a 10 to the power of n. Lightly worked material, 10 to the power of 12. And then heavily worked material will be 10 to the power of 16. Again, the unit is for everything is minus of 2, meter to the power of minus of 4. Okay, so this is a factual type of questions. If you know, you know. Question number 5. Is it true and false? Let's do it one by one. Removing all the dislocation is a practical method to strengthen industrial material. Removing all the dislocation is a practical method. False. It's not a practical method. Theoretically, yes, it's quite good. One can strengthen the material if they remove the dislocation thoroughly. But practically, it's not the possible one. So false. Second question. Dislocation density decrease with plastic deformation. If we do plastic deformation, dislocation will go out of the surface, go to the surface and then annihilate. Yes, okay. Dislocation density decrease because of the presence of the Frankfurt source. So again, it's a false. Strain hardening occur because dislocation impede each other motion. Is it true or false? Strain hardening is taking place because dislocations are impeding each other. Very good, it's true. They are interacting with each other and they are not letting each other to move ahead. The Burgess vector quantify the magnitude of the slip caused by the dislocation. Burgess vector quantify the magnitude of the slip caused by the dislocation. Is it? Burgess vector B vector is quantify the magnitude of the slip that it caused. For example, let's say my material was this, and this is my slip plane, and this is the Burgess vector B vector. So now what is happening that if slip occur, it will produce the additional step, that is this one. This upper part has moved to the right side and this will move to the left side. So this distance that has been created, the step which is created is nothing but a Burgess vector because they will move by that amount. So the Burgess vector quantify the magnitude of the slip occurred by the dislocations. That's right, it's true. So we can write that it's false, false, true, and true. With that, we have solved these questions. If any doubt, let me know. If not, let's move to the next question, question number 6. When two segments of the dislocation loop meet during Frank-Ritz operation, they combine to form a super dislocation, annihilate due to the opposite Burgess vector, create a grain boundary, transform into the twin boundary. Very good, Ramiredi. It's option B. Annihilate due to the opposite Burgess vector. So this was a Frank-Ritz source. A dislocation is created in this. Now it's moving ahead, moving ahead, moving ahead, and then again it will move something like this. Then it will move something like this. So we're talking about this part. So what will happen? They will annihilate due to the opposite Burgess vector. Actually, it's incorrect. None of the answer is correct. So Burgess vector, no. Burgess vector, they all are having the same Burgess vector. They have the signs are different. And that's why it is. So anyway, for time being, we'll consider this, but they will annihilate. That is the thing which we will remember. Let me cut this part because Burgess vector is not gonna change. Okay, let's move ahead. I think it's clear. They are dislocation. See, the tangent vector of this is over this, and tangent vector of this over this. Right. Opposite tangent vector. The sign of the dislocations are different from each other. They are opposite, and that's why they will annihilate each other. Let's move ahead to the question number 7. By the way, if any doubt, please let me know. Okay, you can interrupt me anytime. The question number 7 says the term work hardening is synonymous to which one? Word which is similar to the work hardening. Grain growth, strain hardening, precipitation hardening, or solid solution hardening. So work hardening, very good. That's a strain hardening. We are giving a strain to the material. We are working onto it. Okay, we are doing some cold work. So the work hardening have the same name, the name as strain hardening. Let's move to the question number 8. Here, in a stress strain curve, the elastic modulus after strain hardening. We are talking about the elastic modulus. If I talk about the stress strain curve, it will go something like this. So they are talking that what will happen to the elastic modulus. This. The slope of the stress strain curve. In a stress strain curve, the elastic modulus of the strain hardening. So we are talking about after strain hardening, what will happen? If I do the strain hardening, what will happen? That instead of the yield strength being over here, it will increase further if I strain the material. And now the elastic modulus the Young modulus will increase. From this, if initially was the red curve, after the deformed, if I do the stress strain curve again for the deformed region, it will go something like this, and the sigma y1 yield strength over here, and sigma y2 yield strength over here. So yield strength is increasing. Yield strength is increasing while the slope of the curve will remain same. Elastic modulus is depend upon the bond strength of the material. Okay, it's not gonna change. You created the strain to the material, you are not changing the bond between the two atoms. Okay, so that's why it will remain unchanged. Option C is the right answer over here. While instead of asking for the Young modulus, if I would have asked, instead of asking for the elastic modulus, if I would have asked you the yield strength, then the right answer will be after the strain, yield strength is going to increase. So increase significantly, we can say the option A will be the right answer. Clear? So with that, we have solved these questions. Let's move ahead to the question number 9. If any doubt, please let me know. This is the question number 9. Strain hardening is evident by the dash in the yield strength after the plastic deformation. Increase or decrease? Increase, very good. If I do the plastic deformation, the strain, like the strain hardening if I'm doing, our yield strength is going to increase. We discussed in the last question itself. Next question, the elastic modulus change remain unchanged during the strain hardening. This is also we have discussed. B, very good. It remain unchanged. C, dislocation density during the plastic deformation. Will it increase or will it decrease? Uh, dislocation density during the plastic deformation, we have just now we have read about the Frank rate source. So overall, if I do the plastic deformation, due to the presence of the Frank rate source, the dislocation density will keep on increasing. So here it will be increasing. Right. See, we saw that we saw over here that this initial dislocation has now bifurcated in the two dislocations. One is this part and another one is this one. This is one part and this is another part where both of them again is going to go. So due to the presence of this particular, what we can say that the Frank rate source, the dislocation density during the plastic deformation will keep on growing. It's not that you deform the material and the dislocation density is decreasing. Okay. Let's move ahead. C is done. And the stress required to move the dislocation increase due to the dash with the other dislocation. So one dislocation is there, another dislocation is there. Yeah, it's going to increase due to the interaction between the two dislocations. So the answer will be here, interaction. Very good. It should increase with the interaction with other dislocations. Perfect. So with that, we have solved these 4 questions as the pair. Let's move ahead to the next question, question number 10. Again, it's a true and false based. The strain hardening make the material more ductile but weaker. If I do the strain hardening, they are saying that your material will become the ductile in nature and it will be weaker. It's true or false? See, we have saw false. Very good. We saw here that I did the strain hardening. After that, my yield strength from here y1 it increased to the y2. This increase, there is an increase will be associated. Okay. And since now my material is more harder, its ductility will decrease. Okay. So it's a false. It will become stronger but less ductile, or we can say the more brittle. Dislocation, annihilation is a primary mechanism of the strain hardening. Dislocation, annihilation, they are telling that if you do the strain hardening, your dislocation will annihilate. Very good. It's a false. It's the other way around. It will increase. The elastic modulus decrease after the strain hardening. The elastic modulus is going to decrease after the strain hardening. Elastic modulus, again, that slope of the stress strain curve. Very good. It's a false again. It's going to remain unchanged. A pre-deformed specimen has a higher yield strength than an undeformed one. True? Very good. The strain hardening is a reversible upon annealing. I had the strain hardened specimen. Now I'm doing the annealing on it, that I'm increasing the temperature. I'm trying to remove the dislocations. What do you think? Strain hardening is reversible among annealing. Like whatever the effect of strain hardening was there, if I did the annealing, it will go away. Answer is true. Right. See what we did in the strain hardening. Let us say this is our initial material. It was having some grain size. After the strain hardening, what will happen to the material is that there will be the reduction in the grain size. It will become more fine and finer, and also the dislocations will be created. That too a lot of. Along with that, there will be the lot of point defects will be created. So this is what happening when we do the strain hardening. While if I do the annealing of this particular thing, annealing of this particular material, which I obtained after strain hardening, it will again regain back to the what it was before. So we can say that the answer is true. So these both are opposite phenomena. They are the opposite two different processes. So we can write false, 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 true, and then true. If any doubt in these things, please let me know. If not, let's move ahead to the question number 11. It's math, sorry, MCQ type. When two dislocation on interacting 111 plane combine, not intersecting. When two dislocation on intersecting 111 plane combine, the resulting dislocation is sessile. Because why it is sessile? Its Burgess vector becomes 0. Its slip plane is not a closed pack plane. It annihilate immediately. It transforms into the vacancy. The option D is absolutely irrelevant. The first one, the Burgess vector becomes 0, no. Again, it's not the case. Okay. If we take 1, 1 bar 0, option B, very good. Its slip plane is not the closed pack plane. Right. So with that, we have solved this question with 11. It annihilate immediately. Again, it's an incorrect one. Let's move ahead. Let's go to the question number 12. Now this is related with the strain hardening. Tau is again the shear stress, sorry, critical resolve shear stress. This empirical relation implies that dislocation motion become easier as the dislocation density increases. Shear stress decreases with the dislocation density. Higher dislocation density required higher stress for the plastic deformation. Tau naught represents the stress at the infinite dislocation density. What do you think? Among all these four, which one is the right answer? Uh, let's do it one by one. Tau naught represents the stress at the infinite dislocation density. It's incorrect. It should be the opposite one. There shouldn't be any density, like there shouldn't be any presence of the dislocation, or you can say that the material should be well annealed. Or if in the question it is also written that the specimen is single crystal, not single crystal, uh, yeah, well annealed is perfect word. Then we can say that the tau naught will be the that particular value of that particular material. Now, higher dislocation density required higher stress for the plastic deformation. See, if the dislocation density is high, the tau CRS will be high, and so which is right over here, because if dislocations are more, they will interact with each other more. Since their interaction with each other are more, they will impede each other's motion, and because of that, since their movement is restricted, the plastic deformation is not taking place. So in order for the plastic deformation to take place, it will require more stress, more external force. So the toss CRSS will again increase. So with that, option C is the right answer. You solve the question number 12. Let's move ahead. Let's go to the question number 13. True and false case. The 001, the 001 plane is a favorable plane in FCC crystal. A favorable slip plane in the FCC crystal. So what is a slip plane? The slip plane is a closed back plane, we know. And 001 plane is a favorable slip plane. It's incorrect because this is not the closed back plane. The closed back plane will be the 111. Yeah, very good, Ramir. It's a false. Let's go to the next question. The combining two dislocations always reduce the total energy. Is it? If I have dislocations, those two are going to combine with each other. Will they always lead to the reduction in the total energy? False again. Yeah. Instead of always may reduce the total energy, then it will be the true. Strain hardening is caused by a decrease in the dislocation density. Third question is saying that strain hardening is caused by a decrease in the dislocation density. Very good, it's a false again. A pre-deformed specimen has higher resistance than the undeformed one. I think we already saw this one, and the option is true. Very good. Sessile dislocation can move freely on any slip plane. False. So only one is true, remaining all are false. Let's move ahead to the question number 14. In the copper zinc system, increasing zinc content. So we have the pure copper with us. Now we are adding zinc to it. Increasing zinc, if we are increasing the zinc content, what is going to happen? Yield strength will decrease, increase in the yield strength, no change in mechanical properties, reduce strain field. Which one will be the right answer? Option B, perfect. Increase yield strength, because there will be the strain field produced about the particular, the impurity material which we are going to add, that is zinc. So that is going to create the strain and it will restrict the motion of the dislocation. Either it can attract or it can repel. In both the cases, it's not going to leave the dislocation free. Very good. Let's move ahead to the next question. Question number 15. An interstitial solute atom causes hardening by reducing the number of slip planes, compressing the lattice around it, increasing the dislocation mobility, and forming precipitation. Interstitial solute. Okay, very good. Compressing the lattice around it. It is what the case with the zinc and copper system which we just discussed right now. Let's move ahead to the question number 16. Which solid would cause the most significant hardening in the copper? So among that, if I want my material to be more harder, which one should I add? Nickel, zinc, beryllium, or very good. Option D is the right answer because it's have the highest, more we can say difference in the strain, in the radius. So it's going to cause more strain. So more strain hardening will take place. Okay. Let's move ahead. Let's go to the question number 17. The mean intercept grain size is calculated by counting the grain per unit area, dividing the test line, mean intercept grain size. So our aim is to find the grain size. So how do we find the grain size? Dividing the test line length by the number of grain boundaries intersecting. Option B, right? Perfect. We have a microstructure with us. We'll see that we will draw one line and we'll see how many times it's intersecting the grain boundaries. And based on that, we'll find the grain size of the material. So we'll do the multiple things, multiple times we'll do the same thing. We'll take the mean of that. And so we'll in that way we'll get the grain size of the particular material, a particular microstructure we can say. So option B is the right answer. Let's move ahead to the next question. Question number 18. True and false based. Let's do it one by one. Grain boundary are defect that always weaken a material. Grain boundary is a defect, that is sure. But will it weaken the material? That too always. True or false? It's a false, right? It restricts the motion of the dislocations in the grain boundary, restrict the motion of the dislocation, and so strengthen the material. In single crystals are more prone toward the plastic deformation than the polycrystalline because of the absence of the grain boundaries. Let's move ahead. The Hall-Page relation predicts that yield strength decreases as the grain size decreases. Yield strength will decrease if I decrease the grain size. What do you think? False, right? Very good. It's the opposite. Yield strength will increase as the grain size is decreasing. More is the grain, lesser is the grain size, more is the number of grain. More is the number of grain, more restriction toward the dislocations to move. And the more is the yield stress. Sigma infinity in the Hall-Page equation represent the yield strength of a polycrystalline with infinite grain size. True or false? It's like sigma infinity is a Hall-Page in a Hall-Page relation represent the yield strength of a polycrystalline material with an infinite grain size. It's a true. Infinite, or you can say very large grain size. Okay, well, very well annealed material it should be. That's all. Okay. So in that case, whatever the strength of the material will be, that is a sigma infinity. Very good. The dislocation can freely cross the grain boundary without additional stress. Within the grain, we applied some stress, like the dislocation is moving within the plane at some particular stress. Will we require additional stress or not? Yes, we will require additional stress. That's right. It's a false. The statement here is false. Okay. The linear intercept method required averaging measurement from the multiple test line. Again, we are talking about the grain size one. So that's true that since we are taking the mean, we'll require the number of datas. So here answer is true. We are left with a few questions only. Let's try to solve them. Question number 19. Given a Hall-Page plot, okay, plot is not given with a slope of 500 and the intercept is given. Okay, so we know that sigma y is equal to the sigma infinity plus k upon root d. So what is given to us is that it's the slope is 500 milliampere this. So this is given to us, and the intercept is given to us. Okay, what we need to find, we need to calculate the sigma y for the grain size. Okay, this is our requirement. So how do we do that? Sigma y will be equal to the slope of this curve is nothing but the value of the k. If it's 1 over kd, so 1 over d, so it's a value of the k itself, nothing, right? So if I want to find the sigma y yield strength for the grain size 25, I will substitute all the values. Sigma infinity is given to us 50 MPa plus k, the value is given to us 500 MPa, a micrometer to the power root of micrometer. That's not a problem. We'll substitute the value of the grain size now. The grain size is 25. Again the micrometer. So they will cancel out with each other. What we are left with is 50 plus 500 divided by root 25 is nothing but 5. So we'll write 50 plus 100. This is nothing but 150. So yield strength we have got around 150, corresponding to this grain size of 25. Clear? That's right. So now the option A, the first answer is clear. The first option, the first question is over. The second, they are telling that the grain size needed to achieve the 200 MPa of yield stress. What we got is 150. While the manufacturer want more than 150 yield strength, 150 is not sufficient for them. They want 200. Again, we'll substitute all the values. Sigma y we want 200. It should be equal to the sigma infinity, that is 50 plus 500 MPa divided by root over d. 500, let's not write the unit, root over d. We'll subtract them, what it will get around 150. 500 over root over d. We'll solve this, we'll get the value of d. Whatever the value you will get, it will be in micrometer itself, because this unit is in the micrometer. So whatever the value you will get, based on that we can find that okay, that much grain size is required to get the yield strength of 200 MPa. I hope it's clear. If not, let me know. We'll solve it again. If it's clear, let's go to the next question. Question number 20. Here. In the aluminum copper phase diagram, the theta is the first one. Option B. Okay, very good. The option B is the right answer. AL to CU. Perfect. Okay, let's move ahead. Again, it was a factual based question. 21. The peak hardness occur when the precipitate are large and white space, fine and coherent, fully dissolved, located at the grain boundary. Peak hardness value, we saw that with respect to the time, and we get some hardness value. So it will go something like this. When we are getting this particular peak hardness, what is the microstructure at that particular point? Large and white stage should be the precipitate, or they should be the fine and coherent, fully dissolved, located at the grain boundary. They should not be located at the grain boundary. Very good. The option is P, fine and coherent, and they should not be fully dissolved. Large and white space. If they are large and white space, then the dislocation can easily pass through them just by the bowing mechanism. Okay, so it should be the fine and coherent. Some book also write that it's a semi-coherent. You can, if in the question it's written that the semi-coherent, that too also is a fine. Okay, let's move ahead to the question number 22. Edge hardening can occur without quenching. We don't need to quench to do the edge hardening, is it? We don't need to quench to do the edge hardening. False. Very good. We do the quenching so that we should get the supersaturated solid solution. Without that, we cannot get the precipitate. The higher aging temperature result in the peak hardness, higher peak hardness. So if aging temperature is increased, then the peak hardness will also increase. This is what the question is saying. What do you think? Aging temperature, okay. Let us say we are performing at some T1 temperature. We'll get a curve like this. This is the hardness value and this is the time. I'll get something like this. Now I'm doing something. I'm doing the aging at the temperature T2, which is lower than T1. The temperature is lower. So in that case, what will happen that it will achieve the more hardness value, but again it will require more time. The time required is more, but the hardness value which is there, that is also more. So here, let's see this. The higher aging temperature, that is T1, will result in the higher peak hardness. No, it's incorrect. If I keep on increasing the temperature, the chances of the precipitation growth will be more compared to the lower temperature. Okay, so that it's a false. Lower the temperature, more is the time required, better product you will get. Okay. Better hardness you will get. The solvent line on the phase diagram mark the boundary between the precipitate. Solvent line on the phase diagram mark the boundary below which precipitation occurs. It's true, very good. Below this point, below this particular temperature, below the solvent line, if you quench, you will get the precipitation. So false and true. If any doubt, let me know. Okay, and let's move ahead to the question number 23. Here, the primary driving force for the recrystallization is. Now we are talking about the recovery, recrystallization, and grain growth. Those stuff are going to come now. The primary driving force for the recrystallization is reduction in the grain boundary energy, reduction of the strain energy from the dislocation, increase in the electrical conductivity, elimination of the vacancies. Very good. It's option B. Relief of the strain energy from the dislocation. Elimination of vacancy takes place in the first stage. That is recovery. Increase in the conductivity also take place in the recovery. Reduction in the grain boundary energy is a driving force for the grain growth. Okay. Let's move ahead to the question number 24. Here, during recovery in annealing, which properties is restored first? Tensile strength, electrical conductivity, grain size, or hardness. So recovery we are talking about, okay, in the annealing stage. During the annealing, the first thing that is going to happen is since first stage is the recovery, what is happening that the point defects that those are there, they will annihilate. They will go to either dislocation or the grain boundary or to the surface. Since the point defects are annihilated, point defects are nothing but the scattering center for the electrical conductivity, right? So because of which the electrical conductivity decreases. So if we remove the point defects, the vacancies, then the dislocations is going to then the electrical conductivity will increase further, right? The first thing that is going to happen is the electrical conductivity. We just now discussed that, okay, the dislocations the energy is utilized in the recrystallization, right? So the dislocation density will decrease during the recrystallization stage, and we know that the tensile strength depends lot on the depends lot on the dislocation density. So this thing is going to happen during the recrystallization. Grain size, again we know that it will happen in the grain growth. Hardness is again depend upon the grain size, and again the dislocations. They don't depend that much on the vacancies concentration or the point effects. So the only thing that is going to happen with the property which is first going to restore is the electrical conductivity. So one can use it very properly. Let us say someone don't want their hardness and the tensile strength to change or grain size to change. They only want their electrical conductivity to change. So in that case, what they will do, they will only go for the recovery, not the recrystallization, not the grain growth. Let's move ahead to the next question, question number 25. Okay, we have total 4 more questions left. So the higher degree of prior work, prior cold work, what is going to happen? Increased recrystallization temperature, decreased recrystallization temperature have no effect on recrystallization, prevent grain growth. What is your opinion on that? Option A, increase the recrystallization temperature. Actually, it's the incorrect one. So now see why is it that higher degree of the cold work? We are doing the cold work. See, let us say my first one is not that cold work. It's a very little cold work. Second one is heavily cold work. Due to the cold working, the grain size will decrease. Also, the dislocation will also increase. This is the case 1. This is the case 2. Now you tell me immediately that 1 or 2, which one is having the more energy? Energy of the material, which in which case is the more? Case 1 or case 2? Case 2. Very good. Here the energy is more. Since the energy present in the material itself is more, so the temperature which is externally we have to provide will be the less, because it's already at the higher energy state, right? So what we can say that if we are increasing the cold work, then among this, which one is the correct answer? A, B, C, or D? Option B, right? Very good. The decrease in the recrystallization temperature. Very nice. So with that, we have solved this question. Let's move to the next question, question number 26. Now this is, if you know about the definition, then we will able to answer it very easily. The recrystallization temperature is defined as the temperature at which, definition of the recrystallization temperature. Option B. Very good. It is 50% recrystallization occur in the 1 hour. Okay. Solve this match the pair type. Here what we have is recovery, recrystallization, grain growth, and the effect of prior deformation. Okay. So let's try to match them. Recovery will match with what? Okay. So recovery, if we talk about formation of the new strain-free grain with the low dislocation density replacing the formed crystal. Increase in the average grain size, reducing the grain quantity, lower crystallization temperature due to the higher strain. Point effect annihilation, dislocation rearrangement, but no major changes in microstructure. Option D. Perfect. First one is going to match with the option D. Second, recrystallization temperature. Sorry, recrystallization. Increase in the average grain size, reducing the grain quantity. I don't think so. The formation of the new strain-free grain with the low dislocation density, right? Perfect. It's the option A. Now third one, the grain growth. On B and C, which one will be? It's option B. Increase in the average grain size. Perfect. And the fourth one will match with the C. So we have solved this. Effect of prior deformation, we got to know that lower the regularization temperature. Now, one last final question we have to do is this one. Calculate the reduction in the grain boundary energy per unit volume when the grain size increase from 100 micrometer to 50 micrometer. Now, grain size is increased. Calculate the reduction in the grain boundary energy. How do we? How will we do? We know that the grain boundary, the surface to volume ratio, and the energy we have taken care, it's like 3 times over the diameter multiplied by the gap. This much is the energy which we will get, which is associated with that particular size. So now what is happening that gamma we know we are when the grain size increases from this to this. Let's do the final minus initial. This is the energy which is required. This what we have to calculate. We substitute all the values. It's 0.5 joule per meter square. 3 we can take out. Final diameter is 50. It's in micrometer. Minus initial diameter is 10. Again, it's a micrometer. See, this one will be the more. This one is the less. So overall, we know that the thing will be negative. So if I am increasing the grain size, what is happening that I am releasing the heat. The specimen is releasing the heat. Now the thing is very clear. It's in the same way the way I have shown you over here. Let us say this is my 50 micrometer grain size and this is my 10 micrometer grain size. Since the grain size is less, so the overall the grain boundaries are more. Here they are having more energy. Here they are having less energy. So energy will liberate. Energy will release from this. So with that we can solve this. Let's try to substitute all the values. See, this is in micrometer, so we have, and this was is in the meter. So what we'll do, we will change this also. It will go to the, if I take it to the numerator, then it will be 10 to the power of 6. So what we are getting is 1 to 12 multiplied by 10 to the power of 4 joule per meter cube. This much amount of energy has been released. Clear? So that's how we have solved all the questions that I have planned for today. With this, I hope that all the assignment questions you will easily be able to solve. So let's quickly have a look on all the questions that has been discussed. Recapitulation grain growth we did talk about over here. Again, the recapitulation definition we talk at what is a recapitulation temperature defined as. Then we discuss about that how the recapitulation temperature will vary with the cold working. During what we can say that during the recovery stage, electrical conductivity is a major thing that is going to change. Then we discuss all 3 stages, what and all the things are happening in this. Then we talk about the age hardening process, and for that we discuss about that the peak hardness values at what should be the structure, microstructure, and then we discuss that what is a theta consists of. Then we talk about the Hall page equation, like mostly the strengthening mechanism that has been discussed in this couple of slides. And here we discuss about that the grain size and all. Here we discuss about the strain hardening, sorry, solute hardening, solution hardening. And then here again, yeah, solute atom hardening, the same thing. How they will going to affect the yield strength. Similar, the slip plane and all those things we have discussed over here. How the strain hardening is going to affect the dislocation density and yield strength. This is how the dislocation density is going to affect the yield strength of the material. In the relation way we have brought in the equation. Here we can say that what is a closed pack plane, whether particular thing like whether dislocation is a sessile or glissile in nature. And then we talk about the annealing and the strain hardening phenomena, how well they are reversible or how they are going to affect. If you fill in the blanks questions based upon the strain hardening, again this is again based on the strengthening mechanism. So more or less our discussion was on the strengthening mechanism. Frankrit shows that the how the dislocations are going to create within the material during the plastic deformation, and this is the thing. And then we discuss about the dislocation density, how we will define them, and the practical strengthening mechanisms, and here about the CRSs. These are the list of the content that we have covered in this particular class, in this particular week. So with that, our today's dot solving session is completed. I would like to ask you, do you have any doubt in this particular session, whatever we have discussed, or in the particular week 11 content? If yes, we can discuss them. If no, we can conclude this particular class. Since there is no doubt very good familiarity, then we can conclude this class. One thing I would like to make an announcement that next week, Saturday, we are going to meet regarding the week 12 content. The doubt solving session will be on the week 12 content. And on the Sunday, again we are going to meet, and the discussion will be on the entire week 1 to week 12. There we can discuss the any doubt which you are having, and that will be our final class. So with that, we can conclude today's class. Again, I will remind you that Saturday we are going to have one lecture based on week 12 content, and next week, sorry, on this upcoming Sunday, the next Sunday after that, then we'll have the dot solving session for the entire course. Okay guys, with that we can conclude today's class. Bye bye.